Last talk of the session, Xiang Li from ByteDance Research.
Hello, everyone. My name is Xiang Li, and I'm a dog from ByteDance. Before my talk, I really want to thank the organizers for invitation and feel quite honored to speak here. And I also feel it's necessary to introduce our company, ByteDance. People may wonder what's ByteDance. You may don't know this company, but you must know TikTok and also other very popular is in China. And but it's still difficult to relate TikTok with some quantum physics. It's hard to imagine, actually. But actually, indeed, our companies are doing quantum research. Our company are eager to apply deep learning techniques to many studies. For example, machine translation, robotics, responsible AI, or drug design. And this is where I belong. Our teams will use the neural network-based quantum Carlo to study quantum physics. And I also have my colleagues, Willow and Xiang down there. Okay. Now I will introduce our basic method and show its application to, for example, normal solids, Wiegand crystal, and recently topological insolution. The basic problem we want to solve is actually very simple. We just want to solve the Schrodinger equation of solids, whose Hamiltonian can be easily formulated like this. They involve electrons and ions and their Coulomb interactions. Once this equation is solved, everything is normal. And however, we all know this task is impossible. There are so many electrons in the solids, so this equation cannot be solved exactly. So to simplify the problem, people will usually use independent approximation. In other words, the many-body wave function will be simplified as some product of single particle orbitals. This approximation greatly simplifies the problem. However, we all know it will usually be wrong, especially in strong correlated material such as high T6 conductor, marine material, or the quantum Hall effect. So there is a new method called deep learning variation of Monte Carlo recently in the and provides more possibilities to study this problem. Its core idea is quite simple. We want to go beyond the Hartree-Fock or single particle orbitals. So we use a neural network instead to express the many-body wave function. With the wave function built, we just use the Monte Carlo method to evaluate the energy of our neural network. And we try to optimize the energy, optimize our neural network. And we hope we will finally reach the ground state. In my view, there are some advantages if we use this method. Because the first is that we think that our many-body wave function will be more accurate than Hartree-Fock one because we can incorporate more correlations. And the neural network is very flexible. It can capture distinct quantum physics. And in terms of Monte Carlo itself, Monte Carlo is a very cheap algorithm that shows a very low complexity, about n to the fourth, where n is the number of electrons. However, in comparison, for example, ED, it has scales exponentially and will soon be unreached if we increase the size. So, okay, now I will talk about how we build a neural network to express the many-body wave function. There are some requirements. For example, since we are studying electrons, it should be antisymmetric, and it should be able to capture the correlations. And it should, since we study solids, we need it to be periodic. And so to incorporate the correlations, let me take Hartree-Fock wave function comparison. Hartree-Fock of orbitals is just a superposition of plane waves, very simple. However, we want to go beyond it. So we first include not only one electron position, but all the electron positions as input. And we will include this all informations. We'll let them go through some linear operation and non-linear operations, and the final output is our orbitals. People unfamiliar with the neural networks may be very puzzled. What's the purpose of this linear operation and the non-linear operations? It's hard to understand. However, in short, there is a theory in the deep learning community saying that any continuous function can be expressed using just this kind of structures, any function. And so we can use this theorem to express any many states. And we further import this orbitals into a determinant, and anti-symmetry is also satisfied. Okay, another thing we need to think about is to ensure the periodic. When we translate any electrons by the lattice vectors, should be same. We will need to see. But actually, it's quite simple. Very simple idea. To make it periodic, we just apply a triangular function, for example, sine to the input, and the final output will be automatically periodic. Very simple. And this simple idea can be actually generalized to higher dimensions or more complex lattice shape. For example, let me take 2D honeycomb as an example. And this blue cone is just the Euclidean distance between the origin and the particle there. And to make it periodic, we just change the formula. For example, apply some triangular functions to the component, and the period and the distance will be periodic. Just look at this. And with these two tricks, we can finally construct our many-body wave function. And this is a further sketch of our neural network. This yellow area is just input, the positions of all the actions. It will be converted periodic, and then go through some neural networks to become orbitals. Sometimes we also want to impose some k-point symmetry. I won't talk about that. It's quite tedious. But after we fusing these two channels, we will get our final many-body wave functions. And okay, and the final tedious thing I want to say is just optimization. With although our neural network wave function is built, the other thing we need to do is to evaluate energy and minimize energy of our neural network. It seems a very simple task. However, it's not. For example, this is the energy landscape of energy. You can see there are many local minima, which means there are many intermediate quantum states, which is unstable. And it's hard to know whether after some kind of energy, whether we are in a global minimum or somewhere else. It's hard to know. So in our community, higher order optimization is usually needed. But it's quite tedious, but I just want to mention that optimization is quite challenging. Okay. This method details are quite tedious and very boring. So I will show our results now. We first focus on the initial real solids. So we take the most simple solids, the one-dimensional hydrogen train, as an example. Actually, the ocean hydrogen atoms are lined up and form a train. That's very simple, but it contains various interesting phenomena such as the liquid, molten insulator, or something else. This figure just plot our calculated energy against other higher precision results. And this blue point are neural network results. We can see that maybe hard to see. Our network result outperforms the traditional BMC result and nearly coincides with the most accurate diffusion Monte Carlo method. And we can maintain its accuracy as we push towards the thermodynamic limit, which seems quite promising. And we continue to make our stuff more difficult. For example, we study graphene, one of the most difficult, famous material in the last decades. We calculate its cohesive energy, and it's also close to the experimental. And we finally try to study a true 3D crystal, for example, the lithium hydride. A very simple crystal, but also frequently used as a benchmark. we calculate its energy curve, and it's also close to experimental. Okay, that's the energy result, and we still wonder. Our neural network seems to get a very reasonable energy, but can it capture the features of distinct solids? So we just also study more complex systems. For example, the silicon or the sodium chloride. There are two typical solids of covalent bond or the ionic bond, and we can see that there is an apparent covalent bond between silicon atoms, which seems reasonable, and we can see close shell is formed near the chloride atom, which seems good. And there are also other groups from DeepMind, Google, and Imperial College London using similar neural networks to study weakened crystal in 3D vectors, and also succeed. Okay, I think I've talked enough about definition of real solids. That's the result seems good, but I know it's quite boring to the physicists, and they are all weakly correlated. Even a hyperbola wave function can give them a very good solution. So we want to find some truly strong correlation system to test our neural network to show its power. After several months of survey, we think marine material is a very ideal platform. And for example, when the barrier gets twisted, the most active bands will get flattened, making this system strong correlation. A strong correlation can lead to many interesting phenomena such as molten solitary weakened crystal and anomalous quantum hole. So we first focus on the weakened crystal physics. Take hydrobarrier WS2 example. In these materials, the most active electrons will located at the K value of the beryllium zone, and other bands are split by a larger spin orbital coupling. So an effective Hamiltonian need to be written to express the active electrons. Just looks like a very standard textbook Hamiltonian in solid physics. But when the bands get flattened, the polar interaction will dominate over other terms, leading to possible weakened crystals. And actually, this weakened crystals is captured by STM several years ago. And as we can see, at these figures just plot weakened crystal at different fields. We can see that at different fields, electrons will get crystallized, but also form different charge borders. And we just wonder whether our neural network can capture these charge borders. So, and this is a sketch of our simulation details. We will first make our action positions uniformly distribute the supercell, and we started to optimize its energy. And finally, this is the intermediate states in our training. And after several hundred steps, we can reach the ground state. And this is the final result of our neural network results. All I want to say is it's also very close to it's a coincide with the experimental observation. And the same stories, and in these few years, weakened crystal has outcome more phases. For example, we can push the integer feeding feedings to higher integer, and actually, this is called a weakened molecular crystal proposed from MIT and Berkeley. That at a higher integer feedings, the most remarkable property is that multi-holes will be concentrated at sublattice, make this marine material an array of quantum dots. Very remarkable. And we also use our neural network to do the same calculation, and the result is consistent with STM observation. Okay, so but so far I just reproduced some STM or other high precision results. So we usually want to find something new, and neural network find something new. So we just train to another similar materials, but with a higher six-fold rotation symmetry. And actually, we find something new. Maybe not, maybe maybe a lot beautiful, but we think it's quite beautiful, so we plot it here. For example, the most remarkable thing is that when the system becomes fully polarized, I mean, all the electrons share the same spin, and at all spins, we will see some kind of striped phases. For example, two holes will occupy the adjacent sublattice, while the additional holes will be shared between them. And this behavior is quite similar to the covalent bond in the quantum chemistry textbook. So we just gave a very nickname. We're going to put covalent crystal, just for fun. And okay, now I will talk about fractional chain isolator. It's an unpublished research result of that, but I want to share this. And we all know that fractional chain insulator is recently discovered by Washington Cornell and SJTU and other groups. But although experimental, we have observed this experimentally, but how to understand its mechanics still remains extremely difficult. For now, to the best of my knowledge, ED seems the only way now for us to understand FCA, which is accurate, but as I mentioned before, it's quite expensive. So we just wonder whether our neural network can capture this very difficult physics, and this is our result. We take what 2/3 feeding as an example, and as a system is just the MOT2 can be, and we take a very small supercell as an example. When what we can calculate is ground state spectrum, and the x versus is the index of the different quantum momentum, and the y is just energy difference. We can see there are nearly degenerate states at momentum labeled 0, 1, 2, which is a clear signal of fractional chain isolator. We can also calculate to make sure this statement. We also calculate the energy spectrum over the twist boundary conditions. In other words, we just make sure this system is get, and the three degenerate FCS states will get mixed as we train the twist. And another thing is that we calculated the one body density matrix, and if this system is truly FCI, the density matrix should be uniform, nearly 2/3, and this is also true. And the final orbital is just we analyze our neural network wave function about its component of, for example, how many orbitals are included, how many orbitals of the lowest band are included our neural network with the component of second band. And as you can see, or you have up to more than 90% contains the lowest level of the energy band, and about 5% contains the first band, which seems reasonable. And we can still continue our calculations to other fittings. For example, 1/3 of the 3/5. We can still get the similar results. We can observe FCA at the experimental observed region, which is okay. The final thing is also with not only calculate fractional anomalous control, also fraction control, very long-standing problem in the community. We have already observed many distinct quantized states. However, and there are also many theories explaining these states. However, there seems still lacks a universal solution to this problem. It's quite challenging. So we wonder, as I have already explained, neural network is very flexible. So can neural network be a universal solution to these hard problems? And this is just a sketch of our neural network. We concentrate on the sphere surface of quantum pole. We put a magnetic monopole in the origin and produce a beautiful magnetic field across the surface. And the other things are quite similar to our previous network. And the advantage of our network is that it can include not only the lowest nano level, but it can include all the nano levels of the calculation in SEAL. So, but we still need to solve whether it's whether its energy is not good or not. And there is some results. For example, we calculate 1/3 or the 2/5 billings, and we can see that our neural network energies can outperform, for example, the lowest band ED results. Seems good. And we also wonder, although our energy is good, our neural network be close or the same as the typical classical looping wave function. And we think yes, we calculate that overlap between network and the looping, and the overlap is much near one. And we also can approach slightly larger systems. However, I still have to admit that we usually fail in larger systems with physics. I have to admit. So I think it's a very promising direction, and but there are also much more efforts to do in the future. And we have actually tried other trials. For example, we have tried to study the superconductivity. That we try cooperate as a example, undopped parent material of cooperate. And this is our spin density of cooperate. We can see that we can capture, neural network can capture the antiferromagnetic physics of cooperation. And the orbital shape seems also reasonable. dx squared minus y squared. However, it's quite pain for us to accurately calculate, for example, its spin gap or other physical observable. It's too painful since cooperate contains many electrons. But we are still working on it. Maybe in other, maybe not cooperate, or also WSC2 or graphene in the future. Okay, now I will give an outlook and near the end. In my view, that DLVMC, deep learning VMC, is quite a powerful and a flexible tool to study physics. In 2021, when I first entered my company, there are only works done for molecules, and after just about 3 years or more, more systems are defined by our community, solids, Moray, and topological system. This system are just visited or studied just within several years, which means this method is very promising and easy to use. Yeah, so and this plot is just a plot. This figure plots the growth tendency of between CPU and GPU. And so this blue line is CPU, as we can see in CPU, in which most traditional methods running on has faced a serious bottleneck in the last decades. In contrast, GPU, in which our neural network run on, has growth significantly, which means maybe in the near future, DLVMC will play more and more important roles, and I hope. And that's all. Thanks.
Yeah. For an example, are you studying on a real material Hamiltonian or just like single band Hubbard model?
You mean what?
The Cooper.
Cooper, I use pseudo potentials to neglect the inner core.
Okay, so it's like a real material Hamiltonian to many bands.
Yes.
Okay. Cool. That's a very complicated starting point.
Yeah, so for these Fermi-net type of architecture, a lot of studies for continuous systems.
Yes.
So what are the status of using this kind of architecture for status models?
Yes, actually, we have considered that, but we still don't get very good results yet. But we actually considered it.
Okay.
So what is the fundamental difficulty for
Fundamental difficulty.
Okay.
Because we focus on continuum model.
Okay, cool.
I think it's for the final point, like you said, the large system will fail. What does that mean?
I just mean that for these systems, that our result is worse than, for example, one band ED is and higher than one band ED. So we think it's not accurate now. And that's what I mean.
So how do you have on the large systems? I mean, this comparison seems shaky, right? There's different factors in place. The ED has, it's fitting a different Hamiltonian.
No, they are the same Hamiltonian for this system. ED, we also have ED results for FQHE. Now we just compare these two results, and our ED results even restrict in the lowest level level, we can still reach its energy results for more difficult fields.
I have a question.
Yeah.
Could you tell us more about your company and is it based in the US? Do you hire
Do you offer any
postdocs?
jobs?
Can students apply or do you take postdocs or are you based in the US?
No, I'm based in China.
Oh, you're in the mainland.
Honestly speaking, I earned my PhD in Peking University, originally studying not conventional physics, I study high energy physics. However, I feel and I find a job just by chance, and we started learning this.
Okay, so you came all the way over here just for this conference?
Yes, actually, this is my first time in US.
Oh, okay. Thanks for coming. Okay. It's a long trip for.
Yeah, you can also
It's a
say
short
something about
workshop.
your American branch, so Polar Research. So that's one from American.
Yeah, we have a US branch in San Jose.
Okay, that's what I was thinking is that you must have a branch here in the US.
But like, he's in China, I'm in San Jose. and
Okay.
He comes there for this.
I see, okay. Great, all right. I guess that concludes the session.
Okay, thank you.